Okay. In the last lecture, we have discussed about we are in the hydrocarbon chapter. So in the last chapter, we have actually discussed about the vicinal halides. So if you see the vicinal halide, vicinal dihalides, from the vicinal dihalide, we can get the alkyne preparation. So we have discussed about we have discussed about the how to prepare we have discussed in this chapter, we have discussed about the how to prepare alkanes, how to prepare alkenes or alkenes, and then we are discussing about the how to prepare the alkyne moiety. That is one of the more important molecule is the acetylene. How to synthesize this kind of molecule, acetylene. So if you start from this kind of vicinal dihalide, from where the adjacent one to bromine is also there, and KOH, in the presence of KOH, alcohol and CBr. So we are generating CBr. Then in the presence of NaNH, and then we are getting the acetylene moiety. Okay. Then we are in today's lecture we will discuss about the lecture 9, the hydrocarbon chapter. One possibility is I missed this lecture, so that's why today I'll go for the lecture 9. So the lecture 9, first we'll discuss about the physical properties of the alkyne moiety. So what are the physical properties are you have to know what are the physical properties are available for the alkyne moiety. So let's say if we start from the physical properties of alkyne, follow the some trends of the alkene and the alkanes. What are the so we are here. So actually, due to the internet problem, so it will be very difficult for me. So I'll try to complete this lecture today. So due to so as the same way that it will also follow the same trends like alkene and alkene. So first three members, like the first three members are the gases, and the next 8 are the liquid, and the higher ones are the solid. So the moment you are going from the higher molecular weight, that time the due to the high molecular weight, so it is actually it tends to go for the gases to liquid to solid molecule. But all the alkynes are the colorless, and ethine has characteristics order. The order means the different kinds of smell. So yeah, okay, thank you. So now what happens? So if you see that the lighter molecule, they are the lighter than water even. So alkynes are weakly polar in nature. Why it is saying they're weakly polar in nature, I will also discuss in this lecture. So again, they have some kinds of physical property which is lighter than the water and immiscible with water, but soluble in organic phase. These are the main physical property, that it is not soluble in the aqueous layer. Aqueous layer in the aqueous means water. So it is not visible in water, and it is very means lighter than water also. So if you pour any alkyne moiety, any liquid moiety to the water molecule or aqueous in a beaker, so it has a tendency, it will create two layers. So one is the aqueous layer, another is your compound, that is your organic compound. So that is your organic layer. So your organic layer always will be in the above compared to the aqueous layer. Aqueous layer will be, as aqueous layer is a more heavier, so that's why the density is also high. So that's why if the density is high, then it will always go to the below compared to the which is the least density. Then also but also soluble in organic solvents like ethers, carbon tetrachloride or benzene. So their boiling point, melting point and density increase with increase of the molecular mass. So the moment we are going from the 3 member to 4 member to 8 member, so there will be certain changes of the melting point, boiling point and density. So when you are increasing the molar mass or molecular weight, so that time melting point, boiling point and density also increases. And the chemical properties is what? Chemical properties is these are all the above one is the physical property. So physical property is done. Now we are discussing about the chemical property. So what are the chemical properties are there? So chemical property, if you see, so acidic in nature, they are actually acidic or nature. So in the presence of sodium metal or sodamide is what? So NaNH2. This is called sodamide. NaNH2. So this is called sodamide. These are all the strong base. This is the strong base. This is the strong base, and they react with ethyl molecule, strong base, for to form the sodium acetylide. So what is sodium acetylide? I will come to the also, so how they are forming, and also in the byproduct, as a byproduct, also liberation of the dihydrogen gas. So this reaction have not observed in the case of ethene or ethane, and thus indicating that the ethine is acidic in nature in comparison to ethene and ethane molecule. Why is it so? So has it something to do with the structure or the hybridization? So now we'll come to the reaction mixture, the catalytic, the mechanism. So let's say we start from the acetylene moiety. So acetylene, we know that the acetylene structure is acetylene. Acetylene is the first member of the alkyne moiety, that is very lighter, even lighter than water also. So the acetylene molecule, the chemical formula will be HC triple bond CH plus Na, sodium. Now, so what happened? CH, C triple bond C, C minus, and Na plus. C triple bond Na plus, and plus half molecular weight of hydrogen molecule, half hydrogen. Okay, now so you have this sodium acetylide. So this is called the sodium acetylide. This is called sodium acetylide. Sodium acetylide. Now this sodium acetylide, CH triple bond C minus Na plus, C minus Na plus sodium. So this will form the Na plus C minus, Na plus C minus triple bond C minus Na plus hydrogen. Okay, so this is called disodium acetylide. So this is called disodium because two Na plus is there, one Na plus and two Na plus. So now these two protons are abstracted by the Na plus. Okay, so then what it will have formed? So H plus, and sodium is generating one electron. So this H plus and the electron, it will form the one half molecular of the one molecular hydrogen, not molecular hydrogen, one hydrogen atom. So this is called the disodium. This molecule is called the disodium acetylide. Disodium acetylide. Disodium acetylide. Okay. Now this we have discussed about the acetylene moiety. So now if we go for the one molecular higher than the acetylene, so then it is a propyne, one propyne molecule. So one propyne molecule is, the chemical formula is one propyne. So one propyne molecule is the CH3 C triple bond CH plus Na plus NH2 minus. Now this is just CH3 carbon and C minus Na plus NH3. Now it is a sodium propylite. So now it can again, so it can go again undergo the same kind of disodium acetylide form. Now disodium acetylide form, it is not possible because here only one CH proton is there, but in case of the acetylene moiety, two proton is there, one proton and two proton. So here is only one proton and two proton. So because of two proton present in the acetylene moiety, so that's why the disodium molecule can also form in the case of the acetylene. But in the case of one propyne, only one CH proton is there. So that's why it is not possible for the one propyne. Only one abstraction can happen in the presence of the one propyne and the sodium metal or NaNH2. Now, if you see the next one, so that is called the alkenes, alkynes, and the following the trends in the acidic behavior. Now we'll discuss about the acidic behavior. So we know that the acetylene, so CH triple bond CH. So both the carbon is the sp carbon. Okay, sp hybridized. Now we'll go to the CH2 double bond CH2. So this is a sp2 moiety. This is a sp2 hybridized. Now we have a CH3 molecule. So this is a sp3. Now when you are going from sp3 to sp2 to sp, so there is a increasing of the S character. S character. S character. Okay. Increase of the S character. So now the highest S character is the which one? sp2 acetylene, then acetylene, then ethylene, then ethane. So this is the most highest the acidic character of the in the comparison to the alkene, alkyne, and the alkane molecule. Now you can see the sp is the alkyne is the highest acidic in nature. Now if you compare with the among three other acetylene moiety, alkyne moiety, whether what are the acidic behavior they can show. So if we just compare with the first three molecules of the alkyne moiety, so one is the acetylene, let it be there, acetylene CH triple bond CH. Then yeah, now if we discuss about the first molecule of the first of the then the acetylene, then the one of the CH is replaced by another methyl group, then C, then CH, then there will be two CH3 molecule. Okay. So now you can see the alkyne moiety is this one. Now we have a say one propyne, then we have a two CH3 molecule is there also. So the moment we are going from the one CH3 to two CH3 to one CH3 to two CH3, so there is a hydrogen is gone actually. So that's why when we are going from the one CH3 from the acetylene to one propyne to alkyne, so there will be the decreaseness of the acid character of the alkyne moiety because there is no such acidic proton. So this is the proton, acidic proton. So now you have a why it is highest because you have a two acidic proton. That's why it is more acidic in nature. Now you have only one CH proton. That's why one of the it is less acidic compared to acetylene. Now the third one, that is a two CH3 molecule is there. That is this example. There is no such acidic proton is available here. So that's why it is a very less acidic in nature. Now the addition reaction to the addition reaction. So we have also discussed about the alkene, some of the functionalization for the addition reaction, halogenation reaction, and addition of water, addition of the oxidation reaction, and also some of the addition of water, addition of other ozonolysis. This kind of thing also we have discussed in the alkene moiety. So what about the alkyne moiety? So alkyne contains a triple bond. So alkyne contains a triple bond. So they add up to two molecules of dihydrogen and also halogen halides. Formation of the addition product takes place according to the following step. So let's say this is a simple alkyne moiety. So let's say if we start from the normal example, C triple bond C, and you have a one alkyl halide. Let's say H. Anything HX. Now proton will go, this is a HX means H delta plus and X delta minus. Now you have a proton H plus. Now the proton will go and add to any of the carbon. So now you have a carbon double bond, carbon positive. So this is the hydrogen molecule. Now you have a G molecule. G not X because we have taken X molecule. So let's say X minus is there. Now you have a positive charges here, and this is a nucleophile. Let's say this is a nucleophile, X minus nucleophile. H plus is H plus already added to the carbon, and one positive charge will generate here. Now this X plus will go and add to this positive carbon chain, carbon molecule. Now this C and a hydrogen here. Now double bond. Now here is a one X molecule. Now this is called actually vinyl cation, because the carbon molecule is positively charged, so that's a vinyl carbocation. Vinyl carbo. Now, now we'll go to the additional product. Actually, the additional product form depends upon the stability of the vinyl cation. Addition in unsymmetrical alkyne. So, in the case of symmetrical, whether it will go add to the any of the carbon, anyway you will get the same molecule, same product. Okay. But when you are talking about the unsymmetrical alkyne, it takes place according to the Markovnikov rule. So majority of the reaction of alkynes are the example of the electrophilic addition reaction. So now suppose we have an addition of dihydrogen molecule. So now you have a acetylene moiety, and acetylene with you have a hydrogen molecule and platinum, palladium, nickel. So CH2 double bond CH2. So now you have a olefin. This is called the alkene moiety. So suppose if we start from the acetylene moiety CH triple bond CH, now you have a hydrogen molecule. Now platinum, palladium, nickel. So now you are getting the CH2 double bond CH2. Now this CH2 double bond CH2 under hydrogen pressure, what it will form? It will form the CH3 and CH3 molecule. Okay. So now not only this one. So suppose if we take the another example of the alkyne moiety, so that is the propyne molecule. So suppose if we start from the CH3. So these are all the actually the reaction mechanism. Now the theoretical part is almost completed. So in this lecture and the next lecture also I will go through the some of the organic reaction mechanism and reaction. Then this chapter will get completed. Okay, then we can think about the other chapter or the problem answer session. So now you have a propyne molecule. Now you are adding on one molecule of the hydrogen molecule, and then platinum, palladium, and then nickel. Now you have a CH3, you have a CH, you have a CH2 double bond. This is called propene. Now in the presence of hydrogen molecule, what you are getting? CH3, CH2, and then CH2. This is for propane molecule. Okay, so because one hydrogen will go here and here, then you are getting the double bond. Then the moment another hydrogen molecule comes, then also this double bond will get reduced to propane molecule. Okay, now we'll go to the addition of the halogen molecule. So addition of the halogen molecule depends. Halogen means only we are discussing about the Br2 molecule. We will not discuss about the Cl2 and I2 molecule or fluorine. Fluorine is not possible because it is uncontrollable. You cannot control the reaction or reactivity and the selectivity as well as. Now suppose you have start from the alkyne moiety. Okay, so addition of hydrogen. So let's say if you start from the CH3, so we are taking the unsymmetrical alkene CH3 CH. This is the unsymmetrical alkyne. Now if you add the Br2 molecule, so Br2 in the presence of Br2, so Br2 means actually Br single bond Br. Now these two Br will go to two carbon chain, different. One carbon here, another carbon here. Okay, one bromine will go add this carbon, another bromine will get another carbon. So now what we are getting? So we'll get the CH3 Br, then CH, Br. Also we have a one double bond, because we start from the triple bond. Now we'll add the another molecule of the bromine atom. Now if we add the another bromine atom, so then what we will get? CH3, C, Br. So now we are getting the 1, 1, 1, 1, 2, 2 tetrabromopropane, because 1, 2 and this is 3. So the whole molecule will be 1, 1, 2, 2, because 2 carbon, 2 bromine atom is there. So then tetrabromo, tetrabromopropane. Okay. Now the addition of hydrogen halides. So the addition of hydrogen halide is what? So two molecules of hydrogen halide, that is HCl, HBr and HI, add to alkynes to form gem dihalide, in which two halogens are attached to the same carbon atom. Okay. So suppose you have a acetylene moiety. Suppose you have a acetylene moiety. Now you are adding the HBr. So what it will happen? So you have acetylene moiety, that is a CH triple bond, CH plus HBr. Now if you add the Br2, not Br2, that is another HBr, then what it will form? So if you add the HBr, so then what it will form? It will form the CH3. So proton will go and add to this carbon. Now there will be a generation of the CH, Dr plus Br minus, HBr. Okay. Now the addition of hydrogen halide, that means we are in general discussing about the HBr. Also the same thing also, same trends also follow for the HCl as well as the HI. Okay. So now if we have we are discussing about the acetylene, so that is a symmetrical alkyne. Now if we discuss about the unsymmetrical alkyne, that is a propyne molecule. Suppose if we start from the CH3, C triple bond, CH plus HBr. Now then what we will get? We'll get the CH3, C, E, Y. So because Br can also come here, and this one we can discuss about this one we can explain by the formation of the Markovnikov rule. It will follow. How? So first let's say H plus will go and add to any of the carbon. So let's say there is a possibility of one positive charge here, double bond, then CH2, or another positive charge another thing can happen, that is hydrogen will come and add to the middle carbon, that is CH, and then double bond, and then CH2 plus. As you can see that this is the phenyl carbocation. It is also for, as in the previous slides also we have discussed, when it is going via a carbocation, phenyl carbocation moiety, it depends on the stability of the phenyl carbocation. Okay, so now we have this kind of positive charge is there, and another one positive charge is also here. So now we have so this is the most stable carbocation, because this is a secondary carbocation, this is a primary carbocation. So that's why it is going via this carbocation. Now you have so now you can see, so there is a secondary carbocation generation which happens. Now if we add if we have what are the nucleophile we have now? Now Br minus we have. Now this Br minus can go and add to this carbocation, secondary carbocation. That is the secondary carbocation is the Br minus is here. Now this Br minus will go and add to this secondary carbocation moiety here. Now we are getting the CH3, CBr, then double bond CH2. Now you have another HBr. another H molecule. It will also go via the H plus will come here, then the bromine, the positive charge will generate here. Now what it will form the CH3, C positive. Here it is a Br molecule. Then here it is a CH3. Okay. Now you have a Br minus. Now what you will get? CH3. EBr, and then CH3. Now addition of water. So addition of water is what? Addition of water means as we also here discuss in the case of the alkene moiety. Alkene also the addition of water in the alkene as well as also what to know. We want to know whether when the water is adding to the alkene moiety, what are the products we are getting, and when the addition of water is happening to the acetylene moiety or alkyne moiety, then what are the product we are getting. So if we start from the acetylene, so then we are getting the aldehyde moiety. Only the acetylene when you will add, then only you are getting the aldehyde, but one carbon chain ahead, because if you are starting from the acetylene, then you are getting the aldehyde. But if you start from the one propane, you will end up getting the ketone. We'll discuss this one here. So let's say in water, we have the CH triple bond, CH plus water molecule. Now you have a H plus molecule here. Now this will go and add here CH2 double bond CH OH. Okay, because OH will come here and CH2 will come here. Anywhere you will get this one. So now what it will form? So now you have a H plus, then OH will come here. So CH COH C CH2 CHOH. Okay, now CHOH. Now you have a, now this will go for the tautomerization, and the tautomerization will happen here. Then you will get the aldehyde molecule here. H3 CH H3 CHO. Okay. So now if we just increase another carbon, CH3 C triple bond CH plus water molecule. You have a H plus. So then CH3. So two possibilities there. Two carbocation generation can happen. One is this one, or another product can happen, CH3 C A double bond H2. Now if you add the OH minus, then because this is a primary carbocation and this is a secondary carbocation, so it is more stable, so it will go via this way. So then what you are generating is 3 CH COH and then double bond CH2 is 3 C double bond O and then CH. This is a ketone. But what we are getting aldehyde from where? Acetylene. So only the acetylene moiety if you have, then only you are getting the acetyl aldehyde molecule. But when you have a propane molecule, so then you are generating the ketone moiety. Okay. Now we will go to the, so this example also they have given in your notebook. Now if we start from the, so if you want to get the aromatic compound, and the cyclic polymerization can happen in the presence of high pressure and the red hot iron tube. So ethine means the acetylene moiety. Acetylene, when acetylene we are passing through a red hot iron tube at 873 Kelvin, undergoes cyclic polymerization. So three molecules polymerize to form the benzene molecule, which is the starting molecule for the preparation of the derivatives of benzene. dyes, drugs, and large number of other organic compounds. So now we are getting the, so you can see, so if you start from this one, so what it will form? So let's say, so if you have this kind of triple bond here, so now let's say it will go and attack here, it will go and attack here, and then it will go and attack here. So what they are getting? They are getting the this molecule. This is a benzene molecule. Benzene molecule. So even if you start from the acetylene, still we are getting the benzene molecule in a large amount of weight. So just you need the high temperature for this kind of polymerization can happen. So now if you see the molecule, the molecular orbital, so there is a three double bond is present, right? So three double bond means we know that the parallel overlap is always there whenever you have a double bond molecule. So you have a double bond. Now this is a parallel overlap. This one with this and this with this one, and this is also parallelly overlapping zone is here. Now you can see there is a total 6 orbital is there, and then there is a 6 3 parallel overlap is present here. Now if you see the electronical cloud, electron cloud in the benzene molecule, how? So let's say this is a, you can see the this 3D diagram I have taken from the NCERT book, and you can see it. So in between, let's say this is a blue color, this is a benzene molecule, this is a benzene molecule, and above and below there is a some kind of cover or layers. So this layers is nothing else the electronical cloud. So this is the electronical cloud, and this is also electronical cloud. So how it is happening? So this is the lobes. So what are the lobes are available in the above and the below part? So above part are also generating one electronical cloud. Electron cloud is there. So that means anyway it will come whenever it is coming from outside any nucleophile or electronically rich species, whenever it will come to that point, so there will be some repulsion because of the electronical cloud is also there, and you are also coming with some of the electronically rich species, so there will be some repulsion of this kind of repulsion of the electronical clouds. And the same way when when it is also coming from the below to the means the below of the this low, so there is also a formation of the, there is also repulsion happens. So then we are discussing about the now the last part of this chapter is the preparation of the benzene rings. So I am not going through the further for the theoretical study, so I'll just go through quickly so that we can finish the chapter quickly. So the preparation of the benzene ring, so how it is happening? So decarboxylation of the aromatic acids. So aromatic acids means how we can generate these aromatic acids. So aromatic acids are always available in the natural products also contain some benzoic acid. So if you start from the benzoic acid, so just for an example, if you start from the benzoic acid, and the benzoic acid structure is what? Benzoic acid structure is PA, and then it is a COOH. Now you just replace with, now if you react with the NaOH, then you will get the NaOH. If you hit it with the NaOH, then you will get the sodium benzoate. This is called COONA. Now you add sodium hydroxide, same, and in the presence of calcium hydroxide and heat, calcium oxide and heating, then what you are getting? You are getting actually benzene ring. Then how it is happening? So there is a decarboxylation of this one. So how? So COONA means actually you have this one, COO minus and Na plus. So there is a decarboxylation happens. So decarboxylation happens, then you will get the benzene ring. And the reduction of phenols is there. The phenol is reduced to benzene by passing its vapor over heated zinc dust. So you have a phenol ring, you have a phenol, then you have a zinc dust, and if you heat it in a good way, so then what you will get? The zinc dust, zinc oxide plus benzene ring. Okay, so now we will discuss about the electrophilic substitution reaction. So electrophilic substitution is what? So electrophilic substitution is the commonly electrophilic substitution reaction of arenes are nitration, halogenation, sulfonation and Friedel-Crafts alkylation and acylation reaction in which attacking reagent is an electrophile. So now the nitration reaction is what? So we'll discuss not more than 3-4 example. So only the nitration reaction we'll discuss. So nitration reaction means, so if you start from the simple benzene ring, then we'll end up getting the nitrobenzene. So if you start from the simple benzene ring, now if you add the HNO3 and H2SO4, nitration of this molecule. Now if you say about the so mechanism part, we will not discuss here because mechanism maybe in this stage it is very difficult to understand. So I'll go quickly. So not only the nitrobenzene monosubstituted, you will get the monosubstituted disubstituted also. So ortho as well as the meta also as well as the ortho. So you can end up in getting disubstituted with ortho as well as the meta. And sometimes if you give the more amount of HNO3, then you will get the TNT, trinitrobenzene. TNT. This is called TNT. So trinitrobenzene. This is a explosive. Explosive, you know, you heard about the explosive. You heard about the RDX, right? It is also equivalent to RDX. Explosive, like RDX. So this kind of thing is also going in the DRDO. In DRDO, this kind of molecule people are also generating. So now we are not discussing this one. So now we'll go to the halogenation reaction. Halogenation means if you start from the if you start from the benzene ring in the presence of the any Lewis acid like anhydrous FeCl3, FeBr2, Br3 or LCl3 to yield haloarenes. So haloarenes is what? So haloarenes is nothing. So this is a benzene ring. Now you have a Cl2. So you are getting the chlorobenzene. This is called chlorobenzene. There is only one exclusive one product you will get, chlorobenzene. Now the sulfonation reaction. So sulfonation reaction is what? If you start from the benzene ring and H2SO4. So what you will generate? What you will get? You will get the benzene SO3H. So oleamine what? So heating benzene with a fuming sulfuric acid or oleam. Oleam is the what? Oleam is the, this is a short question. Fuming sulfuric acid. Now the Friedel-Crafts alkylation reaction. So Friedel-Crafts alkylation reaction is when benzene is heated with the chloroalkyl halide in the presence of the anhydrous aluminum chloride, alkyl benzene is formed. So alkyl benzene is what? So if you start from the benzene ring, now you have a C2H5Cl, now anhydrous LCl3. So then what you will get? You will get the C2H5 plus HCl. Okay. Now the Friedel-Crafts acylation reaction. So the reaction of benzene with an acyl halide or acid anhydride in the presence of acyl halides or acid anhydride in the presence of Lewis acid LCl3 yields acyl benzene or acetyl chloride. So if you have a benzene ring and CH3COCl anhydrous LCl3 heated and COCH3 you will get the COCH3. Okay, plus HCl. So now if you have a not only this one, if you have acidic anhydride also, you are getting the COCH3. Friedel-Crafts acylation reaction. So previous one is the Friedel-Crafts alkylation reaction, and this is the Friedel-Crafts alkylation reaction. Alkylation means the alkyl group will come and substituted with one of the hydrogen molecule, and this is the acylation reaction where the COCH3 will come to the benzene. Acylation reaction and acidic anhydride in the presence of acidic anhydride and anhydrous LCl3 you will get the COCH3 plus acetic acid. So in this way I'm stopping this lecture today here, and only one class left. Maybe the next class I'll complete this chapter and maybe the another one class I'll take for the question answer solve section. Thank you.